The city of Konigsberg, known today as Kaliningrad, sat directly on the banks of the Pregel River in Prussia. The Pregel split the city into 4 distinct landmasses, connected to each other by 7 bridges. Legend has it that the residents of Konigsberg, as a sort of game, would try to devise a walk through the city, which used each bridge exactly once. It was Euler who first made progress on the problem. Euler's key insight was that the path taken within each landmass was completely irrelevant to the solution. The only relevant feature of any walk was the sequence of bridges crossed. Euler was able to reformulate the problem in simpler, more exact terms. Each landmass would be a vertex, and each bridge an edge. This mathematical structure is called a graph. Take a moment to look at the graph of the problem. Can you find a route which traverses every edge exactly once and reaches every vertex? In 1736, Euler showed that this was actually impossible. To understand why, we need a more rigorous understanding of what a graph is. We can define a graph as a pair consisting of a set of vertices and a set of edges. In this example, the vertices would be the points W, X, Y, and Z. The edges are the connections between our vertices. An edge is said to be incident with a vertex if that vertex is one of the endpoints of the edge. Note that in the case of a multigraph, or a graph with parallel edges, we need to change our definition of the edge set to an edge multiset, since simple sets don't allow for duplicate elements. We can talk about the order of a graph, which we'll define as the cardinality of the vertex set, and the size of a graph, which we'll define as the count of the edges. Since we have an order of 4 and a size of 7, we call this example graph a 4-7 graph. We also have a notion of traversing the graph. Let's categorize the different methods of graph traversal. The broadest of these categories is the walk, which is just an alternating series of vertices and edges. If a walk starts and ends at the same vertex, we call it closed. A walk in which all the edges are distinct is called a trail. If a trail is also closed, we call it a circuit. A walk in which all the vertices, except for the first and last, are distinct is called a path. We call a closed path a cycle. In the Konigsberg Bridge problem, we don't care about repeated vertices, as long as we visit each vertex at least once, and use each edge exactly once. So our problem reduces to finding a circuit which includes every vertex and every edge. We call such a circuit an Eulerian circuit. A non-trivial connected graph is Eulerian if and only if all of its vertices are of even degree. Let's start by defining our terms. An Eulerian graph is one that contains an Eulerian circuit, and the degree of a vertex is the number of incident edges to that vertex. Suppose G is an Eulerian graph. If we look at an arbitrary vertex of G, excluding the starting and ending vertex, it should be clear that during every encounter we traverse 2 edges, one incoming and one outgoing. Therefore, our arbitrary vertex must be incident with an even number of edges. Next, let's look at our starting vertex. Clearly, we must be incident with at least one outgoing edge. We also don't care how many times we encounter this vertex, but like before, each encounter must be incident with an incoming and outgoing pair of edges. Since this vertex lies on a circuit by definition, we also need to account for one final incoming edge. If we rewrite this expression, it's clear that this vertex will also have an even degree. This proves that it is necessary for every vertex in an Eulerian graph to be of even degree. We have not shown that it is sufficient for every vertex to be of even degree. That is, if every vertex is even, then the graph is Eulerian. Luckily, we do not need the reverse direction of this proof to demonstrate the solution to the Konigsberg bridge problem. Since there are an odd number of bridges in Konigsberg, we know that there must be at least one odd vertex. Therefore, there are no Eulerian circuits in Konigsberg. You can go and visit Kaliningrad today. Two of the original bridges are still standing. But graph theory is about far more than just discovering walks through a city. Graph theory has a wide range of applications, from modeling social networks in sociology to solving problems in computational biology and chemistry. So often, data structures courses fixate on the efficient implementations of graphs and their associated algorithms. While this is undoubtedly important, a lot of insight can be gained by taking a moment to really make sure you understand the underlying mathematics. As an exercise, see if you can prove for yourself that it is sufficient for a non-trivial connected graph to have only vertices of even degree in order to contain an Eulerian circuit.